Let's talk about why the most feared war machine in the skies is being prematurely retired, as if it were an obsolete computer model. Forget the political rhetoric or the false theories about design flaws in military aviation. The real reason the United States prefers to retire its most advanced fighter jets lies in a lethal combination of chemical coatings that disintegrate in the air, processors that overheat while thinking, and engines that can't hide their own heat from the enemy. When news headlines announce that the world's most powerful air force is retiring more than 30 of its flagship Raptor aircraft, many imagine a complete abandonment of stealth. However, the strategic reality is quite different. This isn't about giving up stealth, but rather a cold, hard decision driven by chemical and engineering limitations that make upgrading these pioneering aircraft virtually impossible in the face of modern combat threats. If you're fascinated by military aviation, the science applied to warfare, and the best-kept secrets of the great powers, subscribe to the channel and activate the bell so you don't miss the most impactful technological operations. The first major obstacle that dooms these fighters is the chemical degradation of their electromagnetic absorption materials. The stealth capabilities of the early 5th-generation versions depend on a very delicate formula of polymer coatings applied to the fuselage skin. Designed in the late 1990s, these synthetic compounds proved to be physically very fragile under the rigors of real-world missions. The extreme kinetic friction generated by flying at supersonic speeds, combined with rain, sea spray, and temperature variations in the air, destroys the molecular structure of these protective materials. On the first aircraft of this series, repairing the degraded protective layers required thousands of hours of skilled labor and specialized maintenance for every hour spent in the air, driving operating costs to exorbitant levels. Replacing these outdated materials with the new stack of synthetic composites used in the latest aircraft is not as simple as applying a fresh coat of paint. It would require completely disassembling the exterior structure, redesigning and replacing all the fuselage panels. It's a surgical intervention whose economic cost far outweighs the aircraft's functional value, turning these fighters into veritable white elephants for the military budget. This chemical deterioration of the synthetic skin is compounded by a far more relentless and destructive scientific challenge: the laws of thermodynamics versus new enemy detection networks. The first 5th-generation aircraft were designed to evade only X-band radars, which were the standard for precision guidance in the last century. However, the latest generation of infrared search sensors does not require the aircraft to reflect radio waves to locate it. Flight at high supersonic speeds generates massive aerodynamic drag that heats the leading edges of the wings and the nose of the fuselage to extremely high temperatures. Simultaneously, the continuous expulsion of exhaust gases from the turbines creates a blazing heat energy field that is impossible to conceal. The optical and thermal tracking sensors of enemy fighters detect this temperature contrast against the cold background of the atmosphere from tens of kilometers away, rendering the aircraft's geometry indistinguishable. The third major obstacle this aging technology faces is the architecture of its onboard computers and heat dissipation. Designed with closed and inflexible computer systems from the late 20th century, these aircraft lack the ability to upgrade their software in a modular fashion. Integrating artificial intelligence tools, modern electronic warfare radars, and massive data processors requires enormous electrical power that the aircraft's generators cannot supply. Even if these modern processors could be installed inside the fuselage, it would create an insurmountable thermal problem. State-of-the-art computers generate tons of concentrated heat when processing information in real time. The ambient cooling systems of the original structures lack the space and physical capacity to dissipate such a massive amount of thermal energy without melting the delicate avionics on board or revealing the aircraft's position through radiated heat. If you're passionate about discovering how physics and engineering determine the fate of Earth's most powerful weapons, like this post and share your thoughts on the evolution of air in the comments. The fourth insurmountable obstacle is a matter of simple spatial physics and geometry across the vast distances of the Pacific Ocean. In a potential military conflict over such vast expanses of water, fighter jets need to operate at distances of thousands of kilometers from their island bases or aircraft carriers without constantly relying on vulnerable aerial refueling tankers. However, the combat radius of these early stealth platforms using internal fuel is a mere 900 kilometers, a figure wholly insufficient for the scale of today's maritime theater. To increase operational range and keep fighters airborne for extended missions, the only technical option is to install external fuel tanks mounted beneath the wings. It is precisely at this point that physics imposes an insurmountable geometric barrier. Adding these extra metal tanks irreversibly alters the aircraft's external shape, creating sharp angles that reflect electromagnetic waves directly toward enemy antennas and completely negating its stealth capabilities. Attempting to solve this problem through internal engineering is equally unfeasible. The energy density of conventional aviation fuel makes it impossible to increase flight range without significantly increasing the fuselage volume. Modifying an existing structure to accommodate additional internal tanks would require redesigning the weight distribution, relocating the turbine channels, and altering the aircraft's center of gravity, thus destroying its characteristic extreme agility and aerodynamic maneuverability. Faced with the stark reality of having to spend billions of dollars on thermal, chemical, and computational patches that don't guarantee pilot survival in a sensor-saturated environment, the Strategic Command made a decisive choice. It is infinitely more efficient and safer to reallocate those enormous resources toward the direct development of 6th-generation aircraft and collaborative unmanned platforms designed from the ground up to overcome the physical laws that doomed the 5th generation. The gradual abandonment and strategic withdrawal of the first 5th-generation platforms do not, under any circumstances, represent a step backward in the race for global airspace dominance. On the contrary, this decision marks the formal birth of a new era in military engineering, where the limitations of the past are being overcome through revolutionary scientific concepts. The United States has understood that the only way to maintain an indisputable advantage over the advances of its main rivals is to immediately redirect every available dollar toward the development of 6th-generation projects. At the very heart of this radical transformation are the aircraft of the Next-Generation Air Dominance Program, an initiative designed from the outset to eradicate the thermal, chemical, and computational vulnerabilities that ultimately doomed the pioneering models. One of the most fascinating innovations of this project is the implementation of state-of-the-art variable cycle engines. Unlike traditional turbines that must compromise their performance between fuel efficiency and supersonic speed, these new engines are true mechanical chameleons, capable of dynamically altering their internal airflow during flight. When the aircraft needs to cross vast ocean distances across the Pacific, the engine automatically adjusts its internal configuration to behave like a highly efficient turbofan, reducing fuel consumption to levels never before seen in military aviation. Conversely, when the aircraft enters a hostile combat zone and requires immediate acceleration, the system alters the geometry of its ducts to deliver devastating supersonic thrust. This propulsive versatility completely solves the age-old dilemma of range without the need for external fuel tanks that would obscure the fuselage's shape from enemy radar screens. At the same time, the physics of heat is being rewritten by cutting-edge thermal management systems integrated into the aircraft's structure itself. Instead of allowing aerodynamic friction and processor power to turn the aircraft into an infrared torch easily detected by hostile optical sensors, the new platforms utilize the onboard fuel itself as a high-capacity heat sink. Through microfluidic heat exchangers distributed across the fuselage skin, excess thermal energy from onboard systems is safely transferred to the fuel before it is burned in the combustion chambers, virtually eliminating the external thermal signatures that gave away previous versions. In the realm of computing and data processing, the 6th generation abandons forever the closed architectures that rendered fighters obsolete at the end of the last century. The new platforms are built on a fully modular, open-source foundation that allows for instant updates to combat software, evasion algorithms, and electronic warfare systems, exactly like updating an app on a modern smartphone. If a new threat emerges in the electromagnetic spectrum or an enemy missile battery changes its tracking frequency, engineers can send a code patch directly to the fleet within minutes, ensuring that the aircraft never falls behind the competition's innovations. However, the most profound and awe-inspiring paradigm shift lies in the concept of collaborative unmanned combat. The 6th-generation fighter will no longer fly as a lone wolf in the gloom of the sky. The lead aircraft will act as the mothership and tactical control center for a swarm of autonomous drones powered by advanced artificial intelligence algorithms. These robotic, unmanned aircraft, manufactured at a far lower cost than a conventional fighter, will fly ahead of the main formation, assuming the most dangerous roles in the operational mission. Some of these drones will be equipped with powerful transmitters to saturate enemy radar networks with electronic noise, while others will act as advanced sensors, penetrating even the most heavily protected airspace to identify targets without risking the life of a human pilot. The moment a hostile battery attempts to lock onto a target, the combat drones will absorb the fire or respond with surgically precise strikes, allowing the manned mothership to maintain complete electromagnetic silence and remain entirely undetectable at massive safety distances. This transition to integrated combat ecosystems demonstrates that the U.S. Air Force has chosen to sacrifice the pride of displaying iconic fighter jets in order to ensure true tactical superiority for tomorrow. The machines that once represented the pinnacle of military power are now giving way to a new generation of weapons where molecular science, applied thermodynamics, and artificial intelligence will write the definitive rules of air dominance. Whoever controls information in the electromagnetic spectrum and masters the integration of robotic networks will undoubtedly control the geopolitical destiny of the entire planet. If you've been impressed by understanding the true scientific and financial reasons that are changing the future of modern military aviation, subscribe to the channel immediately, like this content, and share it with your tech-savvy friends to continue discovering the best-kept secrets of global firepower.